Welcome to the Cosmic Pie Podcast, Season 2, Episode 31. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So, Robert,
Uh-oh.
we're getting that close to the holidays.
We are.
We should remind people that we're going to do one more of these.
One more this semester, and then we'll pick up again in January.
So our last podcast will be on December the 17th, so next Tuesday. And then we'll take a little bit of a break for a while. I mean, you're going away, and other things are happening, of course.
Right.
And we hope to be back live on January the 7th.
January 7th.
I believe
Okay.
that's the Tuesday that we would start.
That would be a week before classes start.
That's a week before classes. Yeah. Now, we are broadcasting live from the campus of the University of North Dakota here in Grand Forks. And if you'd like to send in some questions or comments, please use the live chat feature that's running now. And you can interrupt us at any point, of course, with the question, even totally unrelated to what we're talking about at the moment.
Well, I would prefer not that.
Come on, Robert, let's entertain everything.
Okay.
Be flexible. You never know what you'll see in terms of questions.
Be careful
so
with that.
it might make you laugh, Robert.
Oh,
Isn't
yeah.
Isn't that worth it? Put a smile on your face for the day.
Oh, Lordy.
Now, as a disclaimer, would you like to do that?
I'm going to let you do it this
Okay,
time.
so
Thank you.
anything that Robert and I say are totally our own personal opinions and not necessarily opinions of the Department of Physics and Astrophysics, nor the College of Arts and Sciences, nor the University of North Dakota, or anything, no other entity or person thereof, or any other life form in the universe.
Right. Just us.
Just us. That is it.
Yep.
Now, Robert, this gives us a chance. Oh, by the way, I should mention we are going to have more guests on. We didn't plan any around the U.S. Thanksgiving or the fact that the holidays are coming up because people are busy doing their thing. We didn't want to bother people to come on as guests. So we will pick up the guest list and get people to come on. Hopefully, somewhere around the middle of January, we'll start that process once we get into the new year.
I've got a few people to talk to. We might have some good ones.
You know, it's interesting. You just reminded me. I'm just looking at the Physics Today magazine that just came out. I don't know if did you get a chance to see yours?
I've seen it. I haven't looked through it.
Did you notice there's an article in it about masses in around the mantle area? Did you?
Oh, yes, I did.
It's related to some of the stuff we had talked about on the previous.
With Jim.
Yeah.
Jim
So
Van Orman.
it's too bad that article didn't come out before we had Jim on.
Right?
Could ask him some questions about that.
That's the way it usually works. Though.
Yeah, so that's kinda
You
cool.
get some stuff.
Yeah, that's
Comes
sort of
out
afterwards. Yeah, but that's all right.
But,
Maybe we can use that for follow-up with Jim maybe in the future.
Could do that. Yeah.
Ask
If you're
him.
watching, Jim, we may be back in touch
Yeah,
with
so
you.
we better read that article. You probably don't get Physics Today magazine, but we'll send you Robert's copy.
Yeah. The article in question was about the very large low velocity zones and the ultra low velocity zones that are down near the core mantle boundary. So
Yeah, and I've only got about halfway through the article, so
okay.
I'm starting to read it. So hopefully I'll get that covered and probably later on this evening, whatever.
Cool.
That's
I'll
my,
have to look through that.
That's my bedtime reading material. It's whether or not you remember what you read by the next morning. You might have to reread it. When it gets too technical, you kind of zone out, and so. And I don't know.
When I was in the department under James, he was my advisor at Case Western. That was something that they mentioned and laughed about several times with me being a physics background person, is that if you put more than 3 equations in a paper, people will go to sleep on you. And we joke about that in the earth sciences department. Yeah.
Well, Stephen Hawking used to say, his most popular book, The Brief History of Time,
Yeah.
that the publisher, I guess, had told him that for every equation that you put in your book, you have your audience. You cut it in half, the
Right.
number of people that would buy the book. But I think he realized that I just can't do it
You
without
can't
any
do it.
equations. So he said, I'm doing no matter what the consequence, I'm putting a few in there.
Mm-hmm.
So you end up sticking them in. So sometimes, words, you can describe a lot of things, but you never get the precise language that you need in a lot of situations when it involves, physics or mathematics or some kind of science. And so you really need the math.
Especially when you head down into the quantum level.
Oh, for sure.
Stuff like that.
Yeah.
It's only really describable with mathematics.
Yeah. So that's unfortunate because that means a lot of that is left out for a large number of people who don't want to get into the mathematics at that level. And if it's difficult to explain them, it's like I think Richard Feynman said that if you can't explain something to your mother, then you don't really know
You don't really understand it
know
yourself.
the subject
Yeah.
itself well enough, right? That
Right.
that you should.
And that's not, sorry, folks, that's just not the case.
Yeah, it turns out not to be, especially like you mentioned with quantum mechanics. But
Right.
so today we're going to start off with some updates.
Okay.
And the first thing is kind of, the major throughput for NASA itself. And this is the idea of going back to the moon, something we've talked about for many years. In fact, I think the last Apollo 17, that's like around Christmas time to December 1972, I believe.
1972,
it
I
was.
believe, yeah.
So we haven't been back to the moon with humans since that time. Of course, we have been back with robots, essentially. But not with humans. And so there's this push. In fact, I remember, there was talk, when George Bush Sr. was president. So this would have been the early 90s, right? That we were
Right.
going to return to the moon and then on to Mars and this kind of stuff. And then his son brought it back. George Bush Jr.
Yep.
said about returning to the moon and on to Mars. So
And
Obama wanted to go to an asteroid.
yeah,
Because I think, some people suggested he had the opinion is, we've been to the moon, why would we want to go back? Let's go to somewhere new, and let's start with maybe an asteroid. So there was the talk of doing that. It seems like every time you get a change in administration,
right.
you get a change in focus, and that kind of messes things up because administrations can change every 4 years, and typically takes, at least 10 years to develop some type of spacecraft to do something.
Right.
So you keep redoing it.
And it doesn't help that we went from, when we were doing the moon missions, 10% of the budget was going to NASA, to less than 1% is now going to NASA.
Right.
So, when you're given a shoestring to try to do something ambitious, it's either going to take a really long time or it's not going to happen.
Well, the thing is, it takes a lot of money.
It takes a lot of money.
And without the majority of people on board, you're not going to get that money.
Right.
Even if Congress decides to give the money, the next election could,
Wipe it out.
wipe out all those members who are for it. And if the people don't want it, the people don't want
Right.
it. So you're at the mercy of the public, the taxpayer, whether
Yeah.
or not they think it's worth the money and the effort to do the project.
And it's a shame because, for every dollar spent in NASA, so far it's been $7 returned. So,
Well, that's why it's interesting that we have business people involved. You think of Elon Musk.
right.
People have their negative things, their negative thoughts, and their positive thoughts. So a positive thought is that he's able to push the development of technology and not worrying about Congress passing the budget for it.
Right.
Not worrying about the taxpayer, footing out the bill, right, to pay for everything. He can do
Right.
it himself because he has the power, obviously. And that can be a good thing, obviously.
And we got from Mizuho Schwalm, we've got a couple of comments. I imagine the first one came from Bill, and that is, unless there are some equations, I would not read about it. How about that?
Well, what about a novel? Oh, he means scientific work.
Scientific work.
Oh,
I'm thinking.
okay.
And then,
Does the Bible have? No, just kidding.
No. And then there's this time it will really mess up. Afraid he's afraid or she's afraid, given the Artemis mission, and I think that's actually what this is talking about.
Yeah,
is
so
it
this
not?
is the latest update from NASA about the Artemis mission, which is the latest, greatest idea to go back to the moon and eventually go to Mars. But
right.
so the idea of going back to the moon is almost like going to Antarctica. You'd establish a foothold, a beachhead, if you like, a base.
Right.
And it's in a hospitable environment. It's not an inhospitable environment, of course. Like Antarctica, right? You learn to live in isolation. The supplies got to come in, and so on and so forth. So maybe that's a good training. We should put our astronauts in Antarctica for a year or two to see how they do psychologically.
Yeah.
And then they're primed to go to a long duration mission, whether it's back to the moon or on to Mars.
On to Mars, yeah.
Might be a good idea.
And the temperatures would definitely be like winter on winter in Antarctica. So,
Well, did you know
or
that-
Mars anyway?
Like one of the highest temperatures reported on Mars was like 20-some degrees Celsius.
Yeah,
So
down near the equator during the summers.
yeah. So you're not talking about temperatures as low as what you get typically in Antarctica.
Right.
But of course, the average is extremely
The average
cold,
is,
right?
is
So
more like
that's
Antarctica.
that's the maximum,
colder.
yeah.
Yeah, I mean, it's sorry, but you don't have carbon dioxide freezing to ice in Antarctica.
No, exactly. In fact, dry ice, when you think of that, that was the suggestion that was made not that long ago that a lot of the tributaries-like features you see on the surface of Mars, a lot of people right away would say water, right? Mars is a water planet. The water's gone now. It's either locked in the soil or evaporated off or whatever. And other people suggest that maybe some of those features you're looking at is not actually caused by water, H2O, that it's actually like dry ice type of stuff that's moving around.
Well, we've seen on Titan now that there's river-like features from liquid ethane and methane.
And if you admit that, then I guess that you're going on the negative side of the chance of life, and that would hurt the funding. I hate to say it that way, but
But you're not wrong.
yeah,
You're
that's
not wrong.
it. You don't want to make it look like the case for Mars is really difficult for light to have established a foothold, because that makes the government less likely to give you the dollars to continue your research down that avenue.
Right.
So they're always putting a positive spin on things. So is that a bias? Well, yeah, sure, it's a bias. Bias is everywhere. You just got to know, you have to be aware of it. That's it.
Aware of it. Yeah.
So the latest update is involving the next mission in the Artemis project. The first one, Artemis 1, was an unmanned flight to go around the moon a few times and then back to the Earth. And it was unmanned, so not everything was on board the spacecraft. The environmental system wasn't there because there were no humans. But that's also a negative because it wasn't fully tested. So that's a problem. But one of the other things which you see here on the left side is the image taken of the heat shield. So it's like the Apollo capsules where you're riding in on the butt end of it, and that's absorbing, taking the heat, and it chars away and carries that excess heat with it.
Get a blade.
As it burns away. But there was a lot more of the material that got charred or that got torn away from the heat shield as when this capsule came in, and it was to the amount where it's, anyone on board would have survived if they would have had the full environmental system.
Right.
So it's not like they would burnt up, and clearly the capsule survived. You can see it there in the image. But it was a lot more of the degradation of the heat shield than what they had thought.
Right.
And anytime you have something that doesn't look quite right, especially in this type of field where the difference between life and death could be very tiny, you better investigate it fully from an engineering point of view.
And I will point out again, I've mentioned this before when we had James Owens on and talking about rockets. You want things to fail on the tests. You don't want them to fail on the actual deal, so that it's failing on a test is not a failure. It's, yes, this is what we're after.
It also means that things have to be improved before you actually put
actually
people on board, and that's the delay. So the second Artemis flight, Artemis 2, then, is supposed to go up now in the mid-2027.
Okay.
So I should say, sorry, April of 2026. It was scheduled to go up. The last schedule, I think, was late 2025, so less than a year from now. I think it was around October, November timeframe. But now that has shifted roughly 6 months.
Okay.
And that's not surprising. Any type of new project like this, you always have delays. I mean, I remember the first space shuttle was supposed to be launched in the 1970s. It didn't launch till 1981. In fact, one of the early shuttle flights was to boost Skylab into a higher orbit because its orbit was decaying, and NASA wanted to use Skylab in the future to send crew on board and so on.
Didn't make it.
Didn't make it. It came down in, 78 or 79?
Something like that, yeah.
Yeah, so it re-entered and burned up. And the reason for that is the sun was a little bit more active than what we had predicted. That puffs out the Earth's atmosphere a little bit. The Earth's atmosphere is not like a solid. You're above a certain height. Now I'm totally above the atmosphere, or if you're a little bit below it, you're in the atmosphere.
It doesn't work that way.
No, it's sort of a gradual change in the density of the air as you go up.
Right.
And that air, it's alive. It breathes, essentially, that atmosphere. And so if there's a lot more solar activity, it gets energized, it expands outwards. And the Skylab, like a lot of the low Earth orbiting satellites, are in low enough orbit, they're not completely out of the atmosphere. They still get hit air molecules.
Right. They're in space, technically, but there's still enough molecules, enough atoms there that there is a non-negligible drag.
Yeah, they're not in a perfect vacuum condition. Right. And that causes your orbit to decay if you don't boost it, occasionally. And the ISS, International Space Station, the same way.
Yeah.
It comes down, a certain number of kilometers, and then they boost it back up, then it comes back down, then they boost. So if you actually track the altitude of the space station, you'll see it moving up and down almost like a sawtooth-like pattern, right, as they keep boosting it every so often, periodically, to bring it back up. And it's a good thing because that they're able to move the thing, because there's been a few times where they actually had to dodge incoming debris that's in orbit around the Earth that was coming too close for comfort, and they had to move it out of the way a little bit.
Right.
And that risk is only going to increase in the future.
Starlink.
Well, the other thing is the ISS is kind of on its last legs. We don't want to say that, but it is.
It is.
There's not many years left where they're going to, looks like, dump it into the Pacific Ocean. Now, if someone comes along like SpaceX and maybe wants to gear up some kind of rocket onto the space station to boost it to a much, much higher orbit to kind of preserve it for later, they could do that. But I mean, stuff is degrading, the material and the modules, so it's probably not worth it in the end.
Space, folks, is a hostile environment to materials, to equipment, as well as to people. So
yeah, I mean, there's leaks on the space station. And a lot of that's involved when you have rockets that are docking and undocking and that constant motion.
Well, you've got it going around the Earth, so it's in the shadow, and then it's in the sun, and it's got that heating.
Yeah, expanding and contracting. But the fact that there's one module in particular built by a certain country, which I won't name, is leaking.
Right.
And as far as I remember hearing about it, it's sort of an ongoing story that it's probably due to the continuing docking and undocking.
Okay.
And that the flex that occurs when that happens, and eventually that material gives way.
Right.
So
Metal fatigue.
So it's better probably to replace, for safety reason. You have to replace the whole thing, but I mean it's costly, obviously.
Right.
So there's an issue there. So the latest update on this is that the human flight of Artemis 2, which is to go and orbit around the moon and then back, so we're not going to actually land on the moon. That's delayed until April of 26, which pushes then the landing, the first landing since 1972, which is Artemis 3. That landing is now scheduled for the middle of 2027. And I doubt we will make that.
Right.
And the reason why I doubt we'll make it is we don't have a lander yet. How are you going to land if you don't have a lander?
I thought okay, never mind.
Now, 2 companies have been given contracts to develop it. So SpaceX, and that's the Starship stuff that's going now, and Blue Origin.
Oh, okay.
That's the other one.
I was wondering if it was boing, boing, boing.
Yeah, so it's like, okay, 2 companies have it, but where is the lander that's trustworthy enough that we can actually use it from going from lunar orbit down to the surface of the moon?
Where are the tests of it?
Yeah, I don't want to fly it without it being tested. I want to see it go to the moon, land on the moon, come back up again, and no problems, and maybe at least do it once, if not twice.
Right.
Before you want to see human beings on it. So I got a feeling that's going to be pushed for a while. I mean, if you look at Starship and all of its coolness from a technical point of view, it's still not there quite yet that you can trust, doing what you need to do to have people on board and do a nice landing on the surface of the moon and then take off again. All of that stuff, right? But if it lands, if you're going to land on the moon, you're going to land on the moon. Right?
You're going to land one way if you get out, another if you get out there.
Yeah, it depends how hard you land. Now, you may be able to land but never get off. Like you can't then launch.
Like almost happened to the Apollo 11.
Actually. Yes, so you have to be careful of all this kind of stuff. So I think there needs to be a lot more testing, and there's not enough time. I mean, there's a lot of stuff. We have change in administration coming up in January, but even then, to make the mid-2027, I think is really...
That's ambitious.
I wouldn't be surprised it actually gets delayed till the 2030s. To 2030, tell you the truth.
Yeah.
Right. I think that's the case.
I think that's a good time frame. Yeah.
And do we really need to push it to the extreme?
Apollo 11 almost got stranded there. That shows you what happens when you push. Then Apollo 13. This is what happens when you push.
Now, I know other countries are trying to go there, developing technology to send humans to the moon, and that ultimately is going to be the motivation to push it along a little faster. But really, do we need to push it that fast, right? We need to do things more carefully, I think. Anyways, we'll see how that goes.
We'll see how it goes.
Okay, and the next update, because it's something we had talked about in a prior podcast, is the construction of what's going to be the world's largest telescope, optical telescope.
I thought it was 30 meters. It's 39?
It's 39 meters.
Wow.
Now, the 30-meter telescope is the one the United States is spearheading.
Oh, okay.
That's the TMT that they wanted to build on top of Mauna Kea in Hawaii.
Oh,
Now,
that's
of
not going to
course-
happen.
Well, we don't know. It's in court, so I doubt it, but we'll see. And the other one is one that's almost 30 meters in diameter. And it's the large Giant Magellan Telescope that they're building right now in Chile.
Mm-hmm.
The European Southern Observatory wanted to build a large telescope also, but they wanted to make sure theirs was bigger than the United States.
Okay.
At first, they tried to convince the governing bodies in Europe to support the construction of the OWL telescope, OWL,
Okay.
which stands for Overwhelmingly Large Telescope. And that, the best of I remember, was supposed to be 150 meters in diameter.
That would be overwhelmingly large, that's for sure.
So the governments then said, no, that's a little bit too extreme in terms of where you are now. It's essentially a 10-meter class telescope.
Right.
Let's prove the technology a little better and make a smaller telescope. But the idea was, well, we have to beat the Americans
Right.
because they're developing a 30-meter telescope. So we'll develop a 39-meter. That's the story anyways. But the thing about the European telescope is that it's really far ahead. Like it's really, I mean,
Yeah.
the Giant Magellan Telescope is also progressing really well. The 30-meter telescope is on a standstill essentially because they wanted to build it on the top of the Mauna Kea in the Big Island of Hawaii, but there's political, if you
from
like,
the natives, the Hawaiian natives.
don't want that put up there. And so we don't know where it's going to end up. But the other thing is the National Science Foundation, which is one of the major sources of funding in science in the United States, is supporting these telescope projects, but will have decided recently they're only going to support one.
Right.
The Giant Magellan Telescope or the 30-meter. Now, why would you need two? Well, you'd like to have one in each hemisphere. So you can, one in Hawaii studies the northern hemisphere, the one in Chile would study or cover the southern hemisphere, so you get complete sky coverage.
Right.
And you never know what you find on these very large telescopes. Maybe you detect far out in the outer parts of the solar system some massive object that happens to be on a collision course with the Earth. That would give you years of lead time than
Right.
what you otherwise would get from a much smaller telescope. So I'm just thinking what would affect the average person on the street.
Right.
And so maybe that's the difference between life and death, that we'd have enough time to mitigate the risk. Who knows, right?
Who knows?
You never know, right? What happens. So we can only afford one of these telescopes, but they haven't decided which one. I got a feeling if it was, if I had to put some money down on it today, that they're probably going to support the Giant Magellan Telescope because that's actively being constructed and there is no controversy of where it's going in Chile.
Right.
But there is, of course, in it for the TMT, the 30-meter telescope. And because that's more riskier politically, I think NSF is going to go with the better
Right.
odds, right? And I would, right? 'Cause
I would
It's
too.
a lot
I'd
of
hedge
money.
my bets.
You're talking over $1 billion, right, to
Right.
build these things, right? They're not cheap. That's why you need governments to build them, right? Individuals,
Absolutely. I mean,
unless you're Elon Musk.
yeah, and
And he wouldn't put
He
one
would
on the
balk
ground.
at it, too.
He'd put it in space.
He'd
He
put it
wouldn't
in
fool
space.
around with the ground. But to be fair, these telescopes all have the adaptive optics system, right? So they
Mm-hmm.
can mediate some of the blurring effect of Earth's atmosphere, but it's never perfect.
right.
And if you ever want to see how that works, and it uses lasers, you shine lasers up in the sky so it illuminates the sodium atoms that are up there, and you essentially make a spot in the sky that's observed by much smaller telescopes that's near the larger telescope. And you know what the size of that spot is because you know the laser and its properties and what the size would be at the given height above the ground. And you see that spot, if the atmosphere disturbs or distorts that image, you can compensate in the right way to counterbalance that distortion. And you
Yep.
have a computer that's actively pushing and pulling ever so slightly on the back of the mirrors to try to make the surface warp in such a way that the light comes in and reflects to the focal point that you want it to, regardless of what part of the mirror it strikes.
Right. And that's part of the problem is with the atmosphere, it's always shifting that focal point a little bit.
I wonder if the military has this type of system. They got to.
Oh, I'm sure they do.
Imagine ground-based telescopes run by the military looking at spy satellites to try to figure out their capabilities.
Or vice versa.
And you always have to worry about the atmosphere, affecting things. So I'm sure they could have the technology developed way beyond what astronomers are even using.
Right.
And of course, be all top secret. We wouldn't know, but who knows what? I mean, you spend money on stuff.
They've got top men
right? So, but they have a black budget, right?
Right.
So-called, right? So they can spend all this money and we don't know where it goes. We don't know where it is, supposedly. So I don't know.
Yeah.
Who knows? But anyways, so the European Southern Observatory, this is a real image taken, lately of the status of the telescope. And you can see they got like a good part of the dome is constructed already.
Mm-hmm.
So this thing is moving along. In fact, the first light is when you first operate a telescope. That's supposed to take place in 2028. It's not that far along when you think about it. There's still some mirrors that need to be put here to finish the construction.
I was about to say they've already been pouring and polishing mirrors. So
Yeah, definitely
it's moving along.
So we only have 3 years to go. So and this will be, the largest telescope. It's going to operate both at optical and infrared wavelengths.
Okay.
But it's definitely going to be the largest. It'll surpass the telescope that's in the Canary Islands. That's mainly owned by Spain, and Mexico has a minority share of that telescope. So it'll surpass that telescope.
Okay.
And to be the largest in the world. And we'll see how all this plays up. So in some sense, this telescope will grab all the low-hanging fruit, and it'll be operational before even the giant Magellan telescope gets out there.
Right.
Which is unfortunate if you're, thinking about competition between the United States and Europe, for example.
And who's not?
Yeah, well, that's one of the motivation, isn't it?
Right.
To trying to be the first of everything. It is for some, depending on what you're doing.
Depending on what you're doing.
Yeah. So the next update is something we had talked about, I think, in the last podcast, we briefly mentioned. And this is about the Gaia mission. So do you remember the Gaia mission and want to explain a little bit what its main purpose is?
It's the astrometry mission, isn't it? Yeah. So it's actually mapping very carefully the positions of stars, and it's using the different orbital positions of Earth, which it's in orbit around Earth. No, it's at the L2?
L2 position.
Okay.
So it follows along with
So
Earth.
it follows along with Earth.
It's just not direct orbit.
So it uses the baseline of Earth's orbit, essentially, to get how the nearby stars are moving. And it accurately has used geometry to plot these positions, the distances to these stars, to within, the angles it can measure are milli-arc seconds. So I think it's milli, isn't it? Or is it tenths of milli?
It's a very, very, very tiny.
A milli-arc second, if you think about a 1 degree, how small an angle that is, divide that up by 3,600, and that's an arc second. Divide that up by 1,000,000, and you're getting into the realm of where this telescope is able to watch the shift, the change in position of a star. So very important mission, very, very, very nice mission. It's been produced a lot of good data, a lot of good information, and it's dying.
Yeah, so you want to read the statement that's taken from the Gaia's website?
The Gaia spacecraft relies on a cold gas propellant to keep it spinning and scanning the sky. The amount of remaining cold gas decreases by 12 grams per day and is reaching its end in early 2025. The Gaia science observations will therefore end on 15 January 2025, meaning that no more nominal science data will be acquired by Gaia after that date. So basically we've got a month and no more new data.
And that's very unfortunate. One of the hardest things to measure in astronomy is the distances to whatever object you're looking at.
Right. The best way to do it is use simple geometry, which is what Gaia is doing. Allowing, anyway, I should say.
And unfortunately, that of course, only works for nearby objects.
Right. But Gaia pushed the limit on that to much further out than any ground-based telescope could do.
Yeah, for sure. In fact, I'm just going to give you some numbers here. So Gaia has measured the parallax of nearly 2 billion stars.
Wow.
In the latest data release.
Wow.
Which is amazing when you think about it. Now, the telescope, get this, has a precision of 0. And these are in arc seconds, 0.000009 arc seconds.
So 0.9 milli-arc seconds.
So it can measure out distances then based on that out to 100,000 parsecs, 100 kiloparsecs.
Wow.
Now, of
That's
course,
about the size of the Milky Way.
Yeah, It's double the size. So
Okay.
The Milky Way is about 50,000.
So it's measuring everything inside the Milky Way then.
Yeah, but the only thing that would stop that, of course, is the
It's
Milky
gas and dust.
Yes, the Milky Way is full of
Right.
interstellar matter, and that blocks the light coming from distant stars.
but still-
other than that,
Yeah. I mean, that probably means it's got all the stars of the large and small Magellanic Clouds and a couple of other nearby galaxies.
yeah, so that was 5 zeros to the right of the decimal point
Okay, so 9 milliards.
before you get to 9.
Yeah.
So that's the best it can do in terms of its precision.
Wow.
And so to figure out how far you can go in parsecs, you just take 1 and divide that number,
Right.
and that would give you this distance length of about 100 kiloparsecs.
Nice.
Parsec, by the way, is a unit of distance in astronomy. It's equivalent to 3.26 light years approximately, and a light year is the distance that light travels in 1 year.
Mm-hmm.
So 1,000 kiloparsecs then would be 3,260 light years. The conversion.
It's getting us where we know we have solid foundation to say this is how far away these objects are.
So as Robert read, so the mission is going to wind down because it's running out of fuel essentially, right?
Right.
The cold gas it uses for onboard thrusters to orient the spacecraft, and you have to point it in preferred directions.
And you have to point it very precisely
Yeah.
to get that kind of precision.
Yeah, you don't want it wobbling around.
Right.
You're not going to make those type of measurements. So,
So
going along with this idea is this paper that came out recently, and it says the title is Mission Design for Space Telescope Servicing at Sun-Earth L2. Now, let's jump to the next slide.
okay.
Okay. This is the graphic that illustrates what we're talking about when we talk about the L2 position. So these are Lagrangian points where you essentially have, the best way to say it is a neutral position. That is, you're gravitationally pulled in one direction, then some other direction, and you find the point where the poles in all different directions are the same, and they cancel each other out.
Right.
So you're in this sort of neutral Dahl region or whatever you want to call it. And there are several different places you can be for these points. Number one, you could be between the Earth and the Sun. And notice it's fairly close to the Earth. That's the L1 position. So where the Sun and Earth's gravity would essentially cancel each other out. Mm-hmm. And here you really should be thinking of gravitational potential.
Right.
Because that's what we're looking at.
That's
what we're really looking at. But I'm trying to just keep it in sort of simple terms here so maybe those who don't know the science could understand. So you're pulled towards the Sun and you're pulled towards the Earth. And so there's like a happy point where you're pulled equally, like a tug of war, you're pulled equally towards the Sun and towards the Earth. So that would be the L1 position that you see there.
You're not going to fall towards either.
Yes. And then you have another relatively stable position. This is the L2 position. And notice it's on the back side of the Earth relative to the Sun.
Mm-hmm.
And then we have the L3 position, which is on the other side of the Sun relative to the Earth. And then we have an L4 and L5 positions, if you like, on the right or the left side of the orbit of the Earth. Right? You you can see it in the diagram there. It illustrates it more clearly. So a lot of the spacecraft, including the James Webb Space Telescope, is at the L2 positions. Mm-hmm. And that helps because then you can, not looking towards the Sun so much, right? The Earth is there. I mean, the Earth is small, at that distance at the L2 position, which is like 2.5 million kilometers, I think,
Something
from
like
the
that.
Earth. It's on that order. So you're looking out, but you're just not looking back towards the Earth and towards the Sun if you worry about your sensitive detectors. And the idea then is this is a relatively stable position. Not like they're stationary. They move around.
Right.
They're circling around.
They got their own orbit about the center of
around
the
that
zone.
point, right? And the whole thing, of course, is moving around the Sun, right? They're not stationary with respect to the stars. Now, the thing is, at that position, because it's relatively stable, then you have to do a lot less station keeping to keep yourself in a given spot.
You have to expend a lot less fuel.
Yes, to maintain the orientation and the position that you want.
Right.
And so that's the benefit of it. Now, this idea of the paper is to actually have a spacecraft that would go to these positions, like the L2 position, and service spacecraft like the Gaia spacecraft. Now, the Gaia spacecraft wasn't designed for that. And you see on the right panel, the Gaia spacecraft is the thing at the bottom where you have that fan-like structure, and then you got that central tube that you see there. Mm-hmm. The thing that looks like has spider legs that's attached to it, and then there's a piece on the top with sort of like looks like solar panels sticking out on either side. That's the actual service vehicle.
Okay.
Of course, whatever design it ends up having is the design it has, right? It's not necessarily going to be this type of thing.
We've got a question from Wondergoon. How large in terms of area are these Lagrange points? How many things can we stuff into them before we can't stuff more? Stuff them.
Yeah, I can't remember the exact size. They vary depending on which Lagrangian point. Obviously, L4 and L5 is much larger.
They're huge.
But they're large, compared to us, the size of us. But, I mean, there is that consideration. There's too much at the L2 position.
And that's where we like to send stuff. So we've got James Webb there. We've got Gaia there. We've got several other missions that are there. When do we start having to worry about them colliding with each other?
Well, what you'd want to have is probably some way of getting them out of that spot.
Right, kicking. Maybe that's what they ought to use the last bit of propellant for, is kick it out.
Yeah, I never read in detail if they plan to do that or not, but that would be a good idea. See if they can get it out of that position and open up. It's like picking up spots for geostationary satellites.
Right.
There's only so many, and one goes defunct. They try to move it out of there to open up that space.
Right.
And everybody, international agreement where you can put your satellites. And
unless you're a couple of countries.
Well, yeah, whatever.
We won't
but
mention
yeah,
names,
and then the other thing is you don't want too many spacecraft in the L2 position because then they start interfering with each other. Mm-hmm. So you have that sort of thing. And, imagine that like one of the spacecraft actually explodes.
Right.
And you got the shrapnel flying everywhere, and that heads towards the mirror on the James Webb Space Telescope.
Yeah.
So you can, but there's that risk also, right?
You're asking about the area. James Webb is about the size of a tennis court. So these zones, these Lagrange points are, as mentioned, they're fairly large. Exact size, I imagine that probably varies depending on where the moon is and where Mars is, and all the little things like that tug, and they're non-negligible but tiny.
Yeah, and by the time you put a lot of spacecraft in there, it's getting too close for comfort, I think.
Right.
And like I said, if there's any kind of issue with the spacecraft, you don't want it exploding in space, and you have a shotgun blast heading towards your spacecraft that cost $1 trillion in the future to make or something, right? And that area is getting crowded, so you do want to clean that out. So I could imagine in the future we'll have spacecraft that go purposely to the L2 position. And the ideal here is that you'd resurface it. If you run out of fuel, you would supply it with fuel.
Okay.
You'd act like a tanker refuel mission, right? But
or if it's like Gaia where it doesn't have the ability to be refueled like that, you'd just kick it out.
Yeah, exactly.
Preferably on an orbit that will crash it into the moon or Earth.
Well, or an orbit around the sun, right? Ultimately, maybe to enter the sun itself. Right. And that's a good way of getting rid of it. Did you realize that was a way that so it's 1.5 million kilometers to the L2 position. Okay. So it was only off by 1 million. Not bad.
On the scale of space?
And a factor of 2 or something, right? Yeah. But, a lot of this kind of debris, it'd be nice if you send it inbound towards the sun.
Right.
And that was, remember the early proposals of taking all our radioactive nuclear waste?
I remember those.
From the fission reactors and then launching it into space and then sending it towards the sun to get rid of it?
And then somebody figured out the energy requirements because people it's like throwing a bottle out the window of your car, which you should not do. The bottle still moves forward with you. So what does that mean? That means you got to bleed off to send it into the sun. A lot of energy because it's going at the speed of Earth around the sun. So it's going to tend to keep going that fast and not fall in. So it takes a lot of energy to bleed off that much momentum and send it into the sun.
And the other thing that people realize is rockets are not 100% reliable.
What, you mean it could blow up in the atmosphere and scatter that debris everywhere?
Yeah. In fact, there was a lot of protests about, I remember the Cassini mission when it was launched. Mm-hmm. There was protests about not launching it because it has a radioisotope thermoelectric generators on board. Right. In other words, plutonium-238.
Right.
And if that blew up on launch, let's say a half a mile above the ground or a mile above the ground, it would scatter all that radioactive plutonium and contaminate, essentially a huge area of the surface of the Earth. But NASA ensured that the plutonium was safe. Like it was in a capsule that it was designed that if it did blow up, it wouldn't rupture the casing. So you wouldn't have to worry about it.
Well, I've seen the tests of some of these casings, and they do things like fly jets at Mach 2 at it, and it doesn't rupture the casing. So, you know.
You just reminded me of a joke.
Uh-oh.
It's like a black box on an airline.
Uh-huh.
And they said, why don't we just make the whole plane with the same material as a black box if the black box can survive a crash?
Because then it won't get off the ground because it'll be so heavy.
So
That's the easy answer.
If they can make black boxes that survive plane crashes, I'm sure they can design a container that can hold plutonium so that it won't rupture if the rocket exploded on the way up.
Right.
But anyways, that was the great thing. They didn't want this kind of stuff blowing up when you're launching radioactive waste right off the surface of the Earth. So the other alternative was to go
down
to drill holes, and we can't even decide where we're going to do that.
Right.
Right, because Arizona was supposed to be the primary location. Yuma, Arizona. And that was been argued about since the 1970s. People have argued back and forth on that issue. So they just store it, do you realize they just store it?
They're at the plant.
At the plant themselves. Yeah. Eventually we're going to run out of space.
Right.
And it reminds me like space. Remember the show 1999? You can see it on YouTube, of course, and reruns and stuff. But that was the same idea, right? They had all of this nuclear waste really close together, and then a reaction happened, explosion, and it set off a chain reaction, and
blew the moon out of orbit.
Out of orbit of the Earth. And so how do we know that some type of nuclear explosion wouldn't happen outside of the power plants?
Well, because it will melt down and spread out and reduce it below critical mass.
Critical mass. But what kind of a mess that would make?
Oh, make one crazy mess. But the big thing that I remember, and I like pointing this out to people, is one of the big things about these big radioactive dumps like that was planned at Yuma is what happens in the future 10,000 years from now. And people go, so what? We just put a warning sign on there. Well, how well can you read ancient hieroglyphics from Egypt? And that's what we're talking about. Our language will be ancient hieroglyphics to them. And my response is, even if we've nuked ourselves back to the Stone Age, humans are pretty smart. Joe goes into this space, comes back, and his hair falls out, and he dies. Bad mojo. Don't go there. People are pretty smart about figuring these things out. It's pretty bad for poor Joe, but
I thought you were going to go a different way with that. I said, poor Joe, unless we can put that in a capsule and put it in the other camp of the other people we don't like.
Right?
Because they would use, in other words, weaponize it.
Weaponize it. But, people are afraid of nuclear waste, and there's reason to be afraid of it, but there's reason to figure out some way of putting it in one location rather than have it scattered out all over.
What are we going to do with it when those locations fill up? Make them even larger?
I guess.
This is like you're putting off this problem into the future. At some point, it's going to bite us.
The new reactors, the stage 4 reactors, because they can use that waste as fuel.
They have to process it. These are the breeder reactor types?
It's not breeders. It's salt bed. Sodium, liquid molten salt reactors.
Right. Yeah, because you need to do something. So if we can use that then and reduce it down to something that's essentially harmless to the environment, that's the way to go, of course.
So nuclear is not the dirty word, folks. Yeah. It's just we need to figure out something to use this stuff.
Well, it's bad enough in the future. People will be digging, this is a great place to construct and a place to live. And they get digging down and they run into like a landfill, right?
Right.
And see all these cell phones. How many iPhone generations are in the landfill? And they're like, all this heavy metals that leached into the water. Thank you for 200 years in the past for doing what you did, right?
Thank you, Nokia.
This kind of thing. So that's another problem, right? Pollution in general.
So,
anyways, there's an interesting story, Robert, I noticed on spaceweather.com. So let's do a plug for them guys.
Yeah, lovely website. If you're interested in solar weather, what's going on, when auroras might be seen, this is a great site.
And this is the one we mentioned last day when we were updating folks on that T-Core Bohr star, the one that's going to go nova at any moment. They actually have a real-time measurements of the brightness of that star. So we're just waiting. If you see that number all of a sudden change, so you know that it's going nova, it becomes really bright, and then you can get out there and try to look at it yourself.
Right.
Anyways, there was a story on it yesterday that caught my attention, and the title of the story was "Solar Storms Are Driving Farmers Crazy." And you're like, how could they drive farmers crazy? You know, some explosion that happens on the surface of the sun. And the thing was, remember back in May, we had the beautiful northern and actually southern lights if you were down south. You remember that back in May? Had that large display? That was due to a major eruption on the surface of the sun. And those charged particles intercept the Earth. Of course. Yep. They spiral around magnetic field lines, crash into the magnetic poles of the Earth, and they energize the molecules and atoms in our atmosphere. And then at night, of course, they give off light, right? The emission lines.
Well, they give it off during the day, too.
You just can't see it, yeah.
Sun's glaring.
Yeah, so we had this really nice display. A lot of people saw the northern lights all the way down to Florida. I think even down to Cuba and Puerto Rico.
Kind of like the Carrington event on that scale.
So at the same time when this was occurring, farmers were having a problem because it affected the GPS signals that their smart tractors received. Now, if you're a farmer, and I don't mean like just an amateur farmer in your backyard, I mean like big industrial size farming. Yeah. You want to be very efficient with your land use. You want to plant as much crop as you can given the size of the land that's available to you. And how better to do that than have a tractor that's tilling up the field and so on, that's guided by GPS, so it knows essentially where it is precisely at all time, to be able to make the nice long lines, if you think of, for planting or whatever you're doing.
Consider it a giant Roomba, except instead of vacuuming your house, it's plowing it up.
Yeah, exactly. And the thing is, you don't want to waste any land.
Right.
So you want to do it really, really precisely and efficiently. And so GPS is the way to go. Well, it turns out, according to this person, Elaine Randstad, who lives in northern Minnesota, so this is a local story for us.
Right.
She claimed, I think in this article, that about half of all tractors today are these so-called smart tractors that run on GPS. So you can return to your exact position, and you can go over so many feet in one direction to make the next run and so on, and without any wasted space. But when the solar storm happened in May, that disrupted the GPS, and the tractors then went crazy. And the quote here is, our tractors acted like they were demon-possessed, right? And it reminds me of the movie Interstellar.
Oh, okay. I have never seen that movie.
You've never seen that movie?
My daughter tells me I need to see it.
Yeah, and it's more than your daughter now. I'm telling you, you need to watch this, Robert,
so I've got two people
over the
telling me I have
holiday
to watch
break,
Okay.
and then we can discuss it on a future podcast.
Okay.
You see how that works?
I see how it works.
Anyways, there was things going on there where their GPS were acting up and so on, right?
Okay.
So any type of solar storm, potentially will affect the GPS. And, of course, the military would be tracking all this stuff because that's the last thing you need is the GPS system to go out at the start of a major conflict if you're relying on that technology. So in that sense, you really need a backup, a way of doing things when that technology fails or some way of improving it somehow. So we'll see what future developments that has. But that's normal now. There's a lot of conflict on the Earth, unfortunately. And a lot of times they're jamming the GPS signals, which affects not only the people who are actively involved in the war, but they also affect the nearby airlines that are flying in that region.
Right.
Or people are jamming signals just to be mean.
Just to be mean.
They're doing it on purpose just to cause disruption in society. And so maybe we're relying too much on that stuff, right?
Arguable both ways.
Well, you're in the woods, hiking, and you rely on your GPS, and something happens. Oh, you drop your GPS that lands in a brook. And you can't get it; it's gone. You got a handheld GPS unit.
Well,
then
that's
you're
why
stuck.
You bring
You can't
a map and a compass.
Well, that's what I'm saying. You need the backup.
You need a backup. I will agree with that. You always plan on a backup.
There's laws too that you can't. I don't know about the different states, but I know where I'm from. There was a law that you had to have a compass, a working compass. You had to have waterproof matches. All these kind of items you had to have with you if you're out in hunting. Right, so if you got a hunting license to hunt in the fall or something, that you had to have these necessary items with you in case it would save your life someday, right, if you get lost.
Absolutely.
I'm sure they have the similar, laws here in the state of North Dakota and other states. I don't know for sure because I don't hunt here, but
actually, this is America.
Yeah,
you can't tell me what to do.
Yeah, maybe so. But anyways, it's a good idea to have those things, and having the skill to read a map and use a compass could come in handy.
Reminds me I need to teach my children and grandchildren how to do that. But yeah, I was part of my Boy Scouts orienteering team, so that's skill I readily have. So
So people might ask, what does all this stuff you're studying right now, the sun and astronomy and all, how does that affect? I just want to plant my crops and make money. Well, here you go. Here's a connection.
This is how space weather affects you.
And we can track what's happening on the sun, so we can alert people and say, hey, there's this major disruption possible in their GPS system. Maybe this is not the good day to go out and do stuff. Maybe take a day off and go buy some seeds somewhere, or whatever else you do as a farmer. Go look at new equipment somewhere.
Right,
or whatever, right? I mean, this might mean not the day to plant. So there's your direct effect when you're thinking about it.
Right.
That's kind of interesting from that.
I love it. This is good things, Shows you why we need to monitor space weather and all these other little things. Everybody always hears about the meteorites and the asteroids, but rarely do you hear about the sun throwing a temper tantrum and throwing off all the satellites.
Yeah, and this is something that's affecting, people right now. Mm-hmm. And this is an average farmer. You're not talking about, having military equipment that gets affected by whatever, or you're a company that runs some satellite network.
Right.
We're talking about the average person that's affected by this stuff. Okay, so the other item that I wanted to discuss before we run out of time, because the hour is soon up already, is these latest observations taken of Quasar 3C273. So that's a catalog name, the third Cambridge catalog of radio sources, and it's entry number 273 in that catalog. That's the history of it. But this object, this Quasar 3C273, has a wonderful history. Do you remember, Robert, from your astronomy, where 3C273 shows up?
Actually, I don't.
This was the quasar that the spectrum was taken of this object back in the early 1960s before we realized they were quasars. This is the one that Martin Schmidt had figured out.
This is one of the ones then that identified that these were galaxies, not...
Yes, it had very high redshifts, and therefore it must be way beyond the Milky Way. So this is one that put him on the cover of Time magazine.
Okay.
And so he figured out, because no one at first could figure out what the spectrum was, what was the nature of these objects. And in fact, Alan Sandage at the time thought they were blue stars. They were bright enough that they looked like stars, and they were blue in color. And they also emitted lots of radio waves, so he thought they were radio stars. First time ever, because usually a star is a poor emitter of radio waves.
It's too bright.
Well, you think it's too hot on a surface. Yeah, and so most of the light comes out at a very short wavelength. Very little of it comes way out in the radio wavelengths. Right. And so this was really unusual at the time. Turns out that was wrong, that they are not radio stars in our own Milky Way. These are supermassive black holes that are in galaxies very far away. In fact, this 3C273 is nearly 2.5 billion light years away, which is a good thing because it is so bright intrinsically that if it was only within a few thousand light years of the Earth, it would be brighter than our sun.
Right. And would probably be cooking us from the X-ray and ultraviolet.
Yeah, so we don't want that. So that's a good thing, to keep away from that. But anyways, so when we put up the Hubble Space Telescope back in like 1990, once it got repaired, unfortunately, that's another story we could do someday is the history of the telescope.
The Hubble.
One of the things that it did is it looked at the different types of active galaxies like quasars to try to get a better understanding of what is the galaxies that they reside in. What's the host galaxy like? Are they all spirals or ellipticals or maybe a mixture and so on? And so there was a lot of push to examine these type of objects. And it's kind of difficult. If you look at the image on the left top, that's an image taken of a quasar, and you see the big diffraction spikes. Mm-hmm. So the object is point-like in nature, the brightness coming from a very small region.
You see those spikes when you've got one pixel that's split up.
Yes, and what you're seeing is the supporting rods of the secondary mirror. Mm-hmm. And what happens in this, what that tells you right away is a point source. It's not an extended source of light.
Right.
And it also means it's very bright. And so they're star-like in appearance. In fact, the name quasar is just a shortened form of quasar-stellar radio sources. Mm-hmm. And so they reduced that down to quasar. And anyways, so these objects are extremely bright. Well, if you wanted to study the galaxy that they're lying in, the stars in that galaxy is a lot dimmer than the quasar itself. So the analogy is, imagine you're trying to study the light coming from a firefly when it's perched on the edge of a searchlight. And it's shining, both of them shining at you.
There's a firefly there?
Yeah, exactly. So it's very difficult. So you got to have some way of blocking the light. And that's the image that you see in the bottom on the left side. That's a recent image taken from the Hubble Space Telescope using an instrument that has a chronograph.
Okay.
Do you want to explain to people what that is?
Coronagraph is just basically where you put a baffle, a block in the middle of the mirror so that the light from that source, that region can't reach the mirrors to be focused.
And we've shown images in past podcasts from the SOHO spacecraft, which works in a similar way. It has an occulting disk that blocks the light from the photosphere, the visible surface of the sun, allowing us to see us outside of that region. So when there's any type of storms like coronal mass ejections or solar flares, we'll be able to see the signature of that without getting blinded by the sun itself. So by blocking the light of the central bright object allows us to see some of the structure that lies around or in the vicinity of the quasar itself. And that's what this bottom image shows, and also the nice, beautiful false color image you see on the right, a lot of the purple and stuff that you're getting there. And you see a lot of strange structure. You see a jet-like thing that sticks in the bottom right. You see the sort of L-shaped almost, right? And you see a lot of other little filaments and patches and so on. This stuff was really never seen in that detail that you're seeing now before. In fact, the image taken at the top left, where you see the full quasar, it's taken by Wide Field Planetary Camera 2. That's WIF-PIC 2. And that was with the new improved camera to fix the vision of Hubble. The image that's taken in the bottom, those two images are taken by a difference of 22 years in duration. Wow. So you can see any changes that may have taken place over that span. And you do see changes, which is amazing. So things are actively changing on that sort of time scale.
And again, that central black hole is blowing out that much energy. I would expect to see changes.
You would expect.
A short period of time.
In fact, the main jet, not the one you see, but the main jet to the quasar, that's on the order of like 300,000 light years in length.
Wow.
And so that's a big one, and you think of that.
This is why we don't want to be close to one of these things.
No, that's for sure.
So.
And the next slide here is the detailed analysis you see on the right by looking at subtracting off different models, or trying to model the underlying light from the host galaxy and subtracting that to essentially look at the structure that's left behind. And that's the details you see in the bottom part on the right-hand side. And there are some things that are labeled there with different letters and so on, a filament-like structure. So these are sort of bright blobs. And what they are exactly, nobody knows. So speculation is it could be remnants of a nearby or a leftover galaxy has been cannibalized by the larger galaxy that contains that supermassive black hole that is the active nature, the engine, if you like, for this quasar. So just to make sure people understand, when you have a quasar, these active galaxies, what you have essentially is a supermassive black hole. And right outside of the black hole, you have what's called an accretion disk. And material falls towards the center of the galaxy, goes into the accretion disk. And that material spirals around in its orbit, and it's a high-density sort of environment, rubs up against each other, and it causes friction, essentially, gravitational tidal effects.
Right.
And it heats up. And it can heat up to millions of Kelvin, millions of degrees Fahrenheit. And at that temperature, you can emit, X-rays, as well as other types of electromagnetic radiation. And so these things can be extremely bright in those types of wavelengths.
And that's, in fact, why it looks blue to an optical telescope. This is actually X-ray and ultraviolet light that's been redshifted into the blue spectrum.
Yeah, and a lot of times this high-energy light heats up the surrounding dust that's in the accretion disk and a giant torus of dust that they usually have. And this dust heats up, and once it gets heated up, of course, anytime you heat up dust, it emits in the infrared.
Right.
And so you have infrared that can be emitted from these active galaxies. So this one is, number one, historical, because it was the first quasar that was discovered. And the other thing is that you can actually see changes in those structures. So it may have been a smaller, low-mass galaxy that ultimately was cannibalized, and maybe that's supplying the raw fuel to keep this galaxy active.
Right.
In fact, you might ask, well, what about our galaxy, the Milky Way? And if you did ask that, good question. Our galaxy also has a supermassive black hole. It's about 4 million times the mass of the sun, but is not an active galaxy. And the reason for that is
It's cleared out the area around it.
Yeah, it doesn't have the accretion disk. There's a little bit of material that falls in once in a while, but not like this setup that you have in these active galaxies.
Is one of the questions that actually they're trying to answer is, was our galaxy like this one at some point?
Yeah, so in the distant past, our galaxy certainly could have been an active galaxy. We know from JWST images that these black holes formed fairly rapidly now.
Right.
So the idea then is if you form a black hole really fast, right, then what happens, you have leftover debris from the formation of the galaxy, and that could funnel towards the center of these galaxies and ultimately supply the energy that we need, the fuel, if you like, in the accretion disk itself.
Okay.
So the other thing I want to show you was changes in the jet. So over the period of these 22 years, it appears that the jet, that's the part of the jet that's furthest away from the quasar, is actually moving faster than the part that's closer to the quasar.
So it was more energetic actually in the past.
Well, look at the blob. The jet you can see in the top right there. It's not one continuous string of material, right? So there can be different episodes where the quasar was a little bit more active and then died down a little bit and then maybe more active. I mean, who knows, right?
Right.
It's some of the stuff that we're studying even today. The bottom figure on the right-hand side shows the speed of the jet, the apparent speed, as a function of distance along the jet itself. And notice that the speed is the units of the speed of light, c. So you have evidence here for superluminal motion, which is not unusual. It just means the jet is more or less pointed almost directly towards us. And the apparent motion then of the light, as you see it going across the material, right, gives you this illusion of faster than the speed of light.
Right.
But it's just an optical illusion in some sense. It's not real. The light doesn't travel faster than the speed of light, right?
Right.
It would be something weird, right? Not in the vacuum of space.
Not in the vacuum.
That's what we're talking about here.
Okay.
So anyways, if you want to learn more about these type of objects, one way to do that, of course, is to go to institutions of higher learning.
Right.
And, well, coincidentally, we just happen to be at one.
Yeah. So come and join us. And you can join us online via several online degree programs that are offered here at the University of North Dakota. Or you can come by and join us in person and join us on this lovely campus. Come by and see Wayne and I. We love to talk to people. We'd love to talk to you.
Now, remember, our next podcast is a week from today, our last one before the holiday break. And we always leave you with a quote. This quote is actually an excerpt of a paper that was written by Martin Schmidt, the one who uncovered the quasar nature of the spectra that they were looking at. So this is about the title of the paper, 3C273, a star-like object with large redshift. So here, and it was actually published in the journal Nature at the time.
Okay.
And the year of publication, 1963.
Okay.
So,
So we've known about these things for a long time.
For a while now, yeah. So here is the excerpt. Only the detection of irrefutable proper motion or parallax would definitively establish 3C273 as an object within our galaxy. At the present time, however, the explanation in terms of an extragalactic origin seems more direct and less objectable.
I can go along with that.
And he was exactly right. All these years later, he's been proven right over and over again. Anyways, if you like this podcast, please don't forget to give us a thumbs up. And if you do, please join us in the future for the next podcast coming up on December the 17th. Thanks for viewing today.
All right. Thanks, everybody.